I'm president of AWM at Kutztown's campus. And today we will be hearing from Dr. Margaret Reddy, talking about polytopes and Whitney stratified spaces. She's a mathematics professor at the University of Kentucky. And I hope you all enjoy her talk. And you can take it away now.
Okay, and I pressed the recording button, so we'll see what happens. Actually, I don't know where the recording's going, if it's for me or you or what, so whatever. Okay, so thank you for the invitation. So again, I'm going to be speaking about polytopes and Whitney stratified spaces. And I should thank my sponsors. So this is a little bit like my commercial break. So I should thank Institute for Advanced Study in Princeton and also the Simons Foundation, who both these organizations have supported my research. They've been very kind. Okay, so let's start talking about polytopes. And I really love this way to think about polytopes. So these are the famous Platonic solids. So these are three-dimensional polytopes. And what's special about them is they're regular. So for example, so this is sort of a funny thing because traditionally Platonic solids, they're associated with fire, air, earth, water, ether, I can't read this, ether. And so these are regular polytopes. So these are objects in three-dimensional space. These particular ones, at least, were three-dimensional. And you can see that, for example, Earth, also known as the cube, the three-dimensional cube, it has 6 two-dimensional faces, namely the squares. They say 8 points. It's actually 8 vertices, 12 edges. So I'm used to counting things by lower dimension up. So number of vertices, edges, two-dimensional faces, etc. What else can I say about these? The fact that they're regular. So notice any two-dimensional face on these polytopes, they all look the same. So a fancy way to say that is that each of these has a symmetry group and it acts transitively. A quick way to think about that is, for example, you could take the cube and rotate it and you would still see the cube. Again, you can move any facet, two-dimensional face here to any other one. So these are examples of polytopes. And actually now my screen is not moving. So these were due to Theaetetus about 400 BC, and the fact that you can actually prove there are 5 regular three-dimensional polytopes. And I give a reference to Euclid's Elements. This appears in Euclid, and I actually have a picture from the Clay Math Institute of this. And let me see if I can actually do a close-up, because I don't know how much of a close-up you can see this if I zoom in. So can you, oh no, can you actually see this projection on the right-hand side? That is a projection of the octahedron. So this is actually so let me go back to normal. So this is actually a copy of Euclid's Elements from 888. So it's actually in Greek. And go to the Clay Math Institute. They have all of this scanned, though, as I had to point out to them, they only had every other page scanned. They actually have it scanned, but they're not all posted because I needed this page. The numbers on the pages, just so you know, like this is, I think it's 350. It's hard to read. That means actual leaf page number 350. There's a front and a back. If you were to turn this book to the next page, it would say 351 on the right-hand side and nothing on the left. So it's how it was actually numbered. Okay. So let's skip ahead 2,500 years. Why not? And let me actually tell you the real definition of a polytope in general. So we're working in n-dimensional space. And one way you can think of it is there's 2 different descriptions. And one is this convex hull description. You take a finite number of points in space and you take something called the convex hull. And that's one way to describe a polytope. So for example, if you have for the cube, three-dimensional cube in three-dimensional space, if you took 4 vertices and actually 8 vertices total, but 4 up here, 4 down here, take the convex hull, bim, bam, boom, you get the three-dimensional cube. Another way to think of a polytope is when you take intersection of closed half spaces in n-dimensional Euclidean space. So you can think about, like, if I have a hyperplane and I take all points below here and all points to, I guess it's your left here, and all points to the right here, and you can actually cut out something that's bounded, that is an example of a polytope. So this is the two descriptions, the V description for vertex, the H for hyperplanes. And oh, if there's questions in the chat, you should let me know, because somebody wrote something, but I don't know if that's for me or for somebody else. All right, so the next thing we want to talk about with a polytope is something called the F vector. And so what this does is it keeps track of the number of faces by dimension. So let's just look at an example rather than stare too much at the definition. So here I have the prism of a hexagon, and F0 is going to count the number of zero-dimensional faces, in other words, vertices. So you can see I have 6 vertices on the top, 6 on the bottom. That adds up to 12. F1 counts the number of edges. So I have 6 edges on the top because it's one-dimensional faces, 6 on the bottom, and then on the sides, there's actually 6 more edges standing up. So 6 times 3 is 18. Finally, F2 here is counting the number of two-dimensional faces. So I have the top face, two-dimensional face, the bottom, which we can't see, and then these 6 rectangular looking faces going around. 6 plus 2 is 8. So that is the F vector. Any questions on that? Because this is going to be like a main deal for quite some time. Okay, if not, we'll keep going. All right, something else incredibly difficult to read. So this is actually a letter. So let me actually go forward one so I can get the thing I want to say. So this is a letter from 1750 from Euler to Goldbach. And he was interested. So in the middle of this letter again, I mean, I have these slides actually posted on my website, so you can look at them closer afterwards. But he has this thing in the middle, sort of, you can't really see it, but it's there when you get closer. H plus S equals A plus 2. What is this? So here H stands for hydrae plus anguli solidi is equal to ACs plus 2. All right, what is this? So what this says is that hydrae is actually facets. These solid angles are what was termed vertices, and these ACs were edges. I'm sure I'm totally mispronouncing this. So what this says is that if you take the number of two-dimensional faces plus the number of vertices, this is equal to the number of edges plus 2. Or more modern language is this is Euler's relation. So what we do, if we just take the number of vertices, put it to the left-hand side, we get this alternating sum. Number of vertices minus edges plus two-dimensional faces in any three-dimensional polytope is equal to 2. And let's actually check that quick for the octahedron. I didn't write that down, but let's check it for, let's check it for the cube, because we were looking at the cube before. So if we look at vertices, so what is that? Oh no, actually we have one to check. I'm being dumb. Prism of the hexagon, 12, 18, 8. So is it true when we take the alternating sum of this, we get 2? 12 minus 18 plus 8. Ha, shocking, we get 2. So the proof of this is actually due to Descartes from 100 years before. So even though Euler's name is on this, it's actually due to Descartes. All right, to say something more historically about polytopes. So it wasn't up until Schläfli from the 1850s that the idea of four-dimensional polytopes emerged. Before that, everyone was thinking about three-dimensional polytopes. So I've actually listed the 6 convex, regular, four-dimensional polytopes. So this is the analog of Platonic solids, one dimension up. So for example, the 5-cell, that's a fancy name for the four-dimensional simplex, the four-dimensional tetrahedron. The 8th cell is also known as the 4-dimensional cube, etc. And I've listed here this Schläfli symbol. So this actually tells you the structure of these various polytopes. So for example, if we look at let's see, the 4-dimensional cube has Schläfli symbol 433. What that means is that the 2-dimensional faces on this, that first, well, let's go back to a cube. A cube would have Schläfli symbol 4-3. And what that would mean is that each of the faces are squares, 4-sided, 4-gons, and that at every vertex, 3 of them meet. So that's what that beginning part says. So here for this Schläfli symbol 433, it actually says the 2-dimensional faces are squares and that, you know, 3 of them meet at every vertex. I should be a little bit careful. It also says that, for example, you can start reading off the first 2 numbers. The 4-3 tells you things about this, that it's behaving like a cube. And then if you read the next 2 numbers together, the QR, this is actually telling you that we have the tetrahedron is also appearing in this. So it's a way to look at things. So I just wanted to mention that in passing. Okay, so this is an extension. Euler-Poincare-Schläfli is an extension of the Euler relation. So this is for an n-dimensional polytope. So we are way up, you know, whatever dimension you want. And it says that if you take the alternating sum of the number of faces in an n-dimensional polytope, you get this 1 minus minus 1 to the n. So depending upon n, you either get 0 or 2. So for example, for a 3-dimensional polytope, that -1 to the n would be -1, 1 minus minus 1 is 2. So this gives you right back Euler relation, also known as Euler-Poincare. So proofs of this. So actually, the first correct proof is due to Poincare in 1893, and he had to introduce homology groups in algebraic topology. So this started a whole new area of mathematics. Schläfli in 1852, he had an idea that this was correct, actually. But for his proof, he was assuming something that wasn't proved until 1970s, something called shellability of polytopes. It's this idea that you can build a polytope by adding one facet at a time. So facet is the maximal dimensional face. So you keep on adding one face at a time until finally at the last step, you close it up and then it looks like a ball. You know, looks like a beach ball. So if he had that, it would have his name on it. But quite often people do call this Euler-Poincare-Schläfli because of that. And then Bruges-Hermanni actually proved in 1971 that that polytopes are shellable. You can build them in this nice way. Okay, so the question at this point is, what about characterizing these face vectors, F vectors of n-dimensional polytopes? So let's say something about this. So 2 dimensions. So easy. So here we have a triangle, also known as a 3-gon, and then we have a 4-gon. So notice I'm not assuming regularity anymore. Just they are what they are, even though my 3-gon almost looks like equilateral, but doesn't have to be. So what does this have? Number of vertices is 3, edges is 3. Hooray, that's exciting. In the 4-gon, vertices is 4, edges is 4. Wow, that's exciting. And very quickly you could say, in 2 dimensions, we can characterize them. Namely, F0 is equal to F1. Number of vertices is equal to number of edges. And we can actually sketch this in the F0, F1 plane. Namely, it's a ray starting at the point 3,3, heading off into the 1,1 direction. Okay, so we can completely classify F vectors for 2-dimensional polytopes. What about 3-dimensional polytopes? Well, Steinitz in 1906, so a little more than 100 years ago now, actually characterized F vectors of 3-dimensional polytopes. So it lives in this cone. So because we have Euler-Poincar array, F0 minus F1 plus F2 is equal to 2, we can actually solve for the number of edges in terms of the number of vertices in two-dimensional faces. We only need to know 2 out of 3 of those pieces of information to pin it down. So that's why this is sketched in the F0, F2 plane. And again, every one of these lattice points, well, okay, I didn't make every one, but in this cone corresponds to a polytope. So for example, 4, 4, that corresponds to the tetrahedron, which has 4 vertices and 4 triangular facets. And then I have 8, 6, which is, let's see, that's 8 vertices and 6 facets. That corresponds to the cube. And then that 6, 8, that's actually its dual, the octahedron, that has 6 vertices and 8 triangular faces. And then I have the 2 lines. One I labeled blue, simple polytopes. The other one is simplicial. So along that red line, any point there corresponds to a polytope that is simplicial, meaning that all of its faces of any dimension is a simplex. So a triangle, when it's 2-dimensional faces, 3-dimensional faces are, well, actually, this is in 3 dimensions. So the most you can go up to is a triangle. And then the dual, the simple polytopes, anything along that other line, these are polytopes where if you look at any, so for a d-dimensional simplicial polytope, every vertex is going to be incident with d edges, it turns out. So this is the dual picture. Okay, so what about 4 dimensions? We're doing great. We know 2, we know 3, we know 4. No. It turns out already, this is an open question, is to characterize the F vectors for polytopes of dimension 4 or more. It turns out in the case of simplicial polytopes, and by duality simple polytopes, this is actually known, characterizing F vectors of any simplicial polytope is actually known. So I'm going to say something about that just so you know the background on that. Okay, so if we start with something that's so I'm going to go a little bit fast, but then I'm going to get back to earth. So don't be forlorn if I lose you for a while. So let's start with the simplicial complex. For example, you can have, your nice, like, for example, octahedron. So that has nice triangular faces. And so there's something called an H vector, which is you massage the F vector into the H vector. So you stick the F vector as coefficients on some polynomials, and then you multiply everything out, and then you get the H vector. And why would this be nice? Well, here I have the octahedron, and I listed its F vector, and below that is its H vector. So this 1, 6, 12, 8 turns into 1, 3, 3, 1. So there's something nice about this H vector, very nice and symmetric. And it turns out that Kind and Kleinschmidt showed that these numbers, the 1, 3, 3, 1, is related to the shelling of the complex. As you're building things together, building that octahedron one facet at a time, how things are intersecting. It actually tells you about this. This is an invariant of the polytope. And Richard Stanley in 1978 showed that this corresponds to something called the Hilbert series of the Stanley-Reisner ring of the complex. There's a way you can associate an algebraic a ring, polynomial ring, modulo certain relations, and keeping track of certain dimensions. This pops up in the numerator. Okay, and then I just have, for everyone to have it, the G theorem. So this is the thing that actually, this characterization of the F vector of a simplicial polytope. So equivalently is to characterize the H vector, and this is due to Richard Stanley. In one direction, he had to use algebraic geometry methods, actually, and Balera Lee in the other was a geometric construction. And one is that an H vector, you have to have the symmetry occurring. HI is equal to HN minus I. And then there's this other thing called the G part of this. It says that if you take differences of successive coordinates in the H vector, this forms something called an M sequence. And maybe I'll just leave it at that. It has to do with commutative algebra. But anyway, they were able to, pretty high stuff to actually talk about just F vectors of simplicial polytopes. All right, what about things like just getting bounds on F vector entries? Well, Barnett showed that if you're given a simplicial polytope, it's the F vector entries are minimized. And if you have K vertices, the F vector is minimized on something called the stacked polytope. So what it is you start with a tetrahedron of whatever dimension you're in, N, and then you take shallow pyramids over the facets until you have enough vertices. And that's actually the polytope that minimizes the F vector. McMullen showed that as upper bound, that if you're given an n-dimensional polytope with K vertices, that you can maximize the F vector entries by something called the cyclic polytope. So what this is you have something called the moment curve. So this is the curve that's has entries t squared, t to the third, up to t to the n. You take K points on this very twisty curve. So they're in generic position. You take the convex hull. This actually maximizes the F vector entries. And then Stanley showed a similar kind of upper bound result for something called simplicial spheres, a nice decomposition of the sphere into simplices. Okay. And then I mentioned some recent work. I'm just going to pass by fast. I mean, this is like upper bound, lower bound theorem for various other objects people have studied. All right, so flag vectors. So at this point, when you start thinking about these things, you realize things are sort of stalled because the F vector is very loose. You're just keeping track of number of faces by dimension. So what we want to do is keep track of something called the flag F vector. So this is flags of faces, how things are connected more. So again, rather than focusing on the definition, let's look at an example. So we're going to look at certain chains of faces. So, all right, so here I have again the prism of the hexagon. And so let's look at this column that's labeled FS. So we're going to take certain subsets of the dimensional faces and see how many we have. So first is, what is F empty? Counting the empty face. There's always one of nothing. So that's one. F0 is 12. We have 12 vertices. F1 is 18, number of edges. F2, number of two-dimensional faces. That is 8. So again, this is the flag vector entries correspond to actually exactly the same as the F vector. So it contains that. Okay, now we get interesting. F01, what is that? So we have to look at pairs of a zero-dimensional face and a one-dimensional face that are incident with each other. So this is a nice polytope because if you look at any vertex, it always is adjacent to 3 edges, 3 one-dimensional faces. So if I just take 3 times the number of vertices, I get F01. So 3 times 12 is 36. F02 is the number of vertex two-dimensional face pairs. And again, this is actually nice, simple polytope. Every vertex is incident with 3 two-dimensional faces. So F02, again, it's going to be 3 times the number of vertices, 36. F12 is the number of edge two-face pairs. Notice every edge in a 3-dimensional polytope is going to be incident with 2 faces. So if you just take 2 times the number of edges, you're going to get 36. 2 times 18 is 36. Finally, F012, this is also known as the full flag. So this counts the number of vertex, edge, two-face triples where everything is all connected. So I can recycle the F01. So I have a vertex edge pairs, 36 of those. And then once I have an edge, that's incident with 2 two-dimensional faces, 2 times 36, 72. So that first column, that's known as the flag F vector. Then the next column is actually the flag H vector. And what this is, it's a certain alternating sum of the flag F vector entries. And so, for example, well, why don't I just leave it at that? So this is a way to compute this. And as you can see, sort of a surprising thing happens with this definition is that you get a symmetric sequence for you get 1, 11, 17, 7, 7, 17, 11, 1. So this is a result of Stanley that actually the flag H vector is symmetric. So for example, you see H empty is the same as H0, 1, 2. H0 is the same as H1, 2, etc. We have this nice symmetry. So the next thing we want to do is we want to encode this information. So remember that when we were computing the flag vector, these subsets were subsets of the possible dimensional faces. So here we had 0, 1, or 2-dimensional faces. So we would like to encode that subset with this U sub S. So there's 2 letters here, A and B. So A is for absent and B is for be there. So it really is. So for example, if I want to encode the subset 0, 1 over here, if I can use my mouse, 0, 1, well, what is that? The 0's in, B for be there, the 1 is in, B for be there, the 2 is absent from that subset. So A for absent. So we encode that with BBA. And now what we're going to do with each of these numbers, we're going to make that the coefficient on the non-commutative monomial, this word in A's and B's, that encodes the subset. And we add them up. And this is called the AB index. All right, so let's write this down on the next slide. So you're going to see on the next slide this 1AA plus 11 BAA, etc. It's a mess. So far we say, okay, whatever. So there it is. But now we're going to do something very funny, which is in the second line here, we're going to factor out an A plus B cubed. Now remember, A and B are non-commutative variables here. So when I multiply out A plus B cubed, I'm going to get A times A times A plus A times B plus A times B times A plus B times A times A. Like I can't move letters around. I have to keep them in the same relative order. So when you have A plus B cubed, that actually pulls 1 off of the coefficients on each of these monomials. So A plus B cubed pulls a 1 off of the AAA, so it's gone. Here, this 11 BAA, one of those BAAs is contained in this A plus B cubed, and I get a 10, etc. So I have all that. So the next step is there any other way we can write this? Well, one thing to notice is we have these numbers here, 10, 16, 6. Does anybody know anything about 10, 16, and 6? Is there any nice relation among those numbers? I see Vanessa going like this. Okay, so 16 is 10 plus 6. So that's good because that gives us a hint about what's going on. So notice here, if we look here at the 6 AAB, this ends in an alternating word AB. This, what else? This 16 ends in an alternating word BA. This 6 BBA, that ends in a BA. The 16 BAB, that ends in an alternating word AB. So if we take out 6 times, and let's put at the end here, AB plus BA, some alternating thing, times the rest, A plus B, that actually is going to pull a 6 off of anything that ends in an alternating BA or AB. So it's going to pull 6 off of here, 6 off of here, 6 off of here, and 6 off of here. And what's left is going to be something that can be factored as 10 times. Now everything left is going to have alternating in the front, this A, B, and BA, and then times A plus B. So now let's do the magic. Let's let C be A plus B. So it's a degree 1 non-commutative variable. D be AB plus BA. That's degree 2. And then we have written the prism of the hexagon as C cubed plus 6CD plus 10DC. This is called the CD index. All right. So one thing to notice is, okay, we have this thing. Can we go back? can we actually go back and get the flag H and flag F information? The answer is yeah. If you're given the CD index of a polytope, you just replace the C with A plus B and any D with AB plus BA. So you can get back to multiplying this all out. So you get back to flag H. And in fact, I never mentioned this, is that if this would let me go backwards, come on. Oh, come on, computer. It's not letting me do anything. Ah, that's bad, bad, bad. Let's see. I don't know why it's doing this. Ooh, it just stopped. Maybe I was touching things too much. Let's see. Okay, let's try something. Let's try. I'm going to just try sharing again. I don't know. I click something. View full screen. I might have erased the page. Yeah, that's exciting. I did that the other day. Okay. Something got erased. Oh, whoop, let's go back. Oh, you know, it's slow. That's what's going on here. Oh, I'm so sorry. Oh, something strange happened. Ah, see, I had this happen the other day. Okay, you know what? Ha 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 ha. That's very bad. Okay, so something erased. So I have a backup plan. All right, small commercial. This happened to me the other day. So let me share. This is what we have learned. We always have to have backup plans because things like this happen. Okay, this won't be as beautiful, but at least it'll be. Come on, share, share, share. Well, it claims I'm sharing. Do you actually see? Oh no, oh, you get to see the end. That's exciting. Okay, let's see. Let's go back, back. Okay, we're back. Go back, go back, go back. Okay. Let's see. Okay, so here we have the CD index. So, okay, this one's working much better. Oh, this is a faster one. That's weird. All right, so much for that. Yeah, so I was saying you can always go backwards, by substituting. And what I didn't mention is actually even going from these flag H, you can go back to the flag F entries. So for example, that entry F0, that 12 is equal to 11 plus 1. That 18, that's 17 plus 1. The 36 is actually going to be any H value that is a subset of 0, 1. So it's going to be H empty plus H0 plus H1 plus H01. So you can always go backwards so you don't lose any information. But notice it's a lot less entries. We started with 8 entries and then, unstable. And then we cut back, the flag H went to 4. And now we're down to a Fibonacci many, 3 entries. So the CD index, you should feel like, great, we've really compacted all this information down. So let's continue with this. All right. So the question is, when do we have a CD index? When can we take this AB index information, the flag vector information, and write it this way? It turns out for any polytope, you can always do this. And there's a more general setting called an Eulerian Poset, which is, so again, this is something called a partially ordered set. You can take the faces of your polytope and order them by inclusion, and it gives you an object, and it's called a poset. And it turns out that there's something called the Eulerian Condition, which says that if you look in any subinterval and the number of elements that are of even rank is equal to odd rank, that's equivalent to Eulerianness. There's another way to talk about with Mobius function, but I will perhaps skip that. I see something in the chat. I don't know if there's a question or not. Is there a question? I see the number 2 chat question. Oh, somebody said, I see slides. I do too. Thank you. So, okay, some CD history. So Bayer and Balera actually showed the generalized dense Somerville relations. They determined all possible linear relations that hold among the flag vector entries. So Euler relation is one of them, this alternating sum. Bayer and Clapper actually showed that the CD index exists. So the fact, and in fact, that not only that, it forms a basis for the space of the generalized Den-Somerville relations. It's also known as the goddess space because it looks like goddess, GDDS. Mark Pertil, in his dissertation, looked at particular cases, CD index of the n-dimensional simplex, so higher dimensional tetrahedron, and n-dimensional cube. And he actually was able to describe what those coefficients meant in terms of something called Andre and signed Andre permutations. And Richard Stanley showed for a face lattice of a polytope, more generally some fancy thing called a spherically shellable face poset of a regular CW complex, that the CD index has non-negative coefficients. So this starts making it interesting when people say, you know, what do these count? When you start having anything in combinatorics that's non-negative, what does this count? All right, come on. Not again. Why is this stopping? It's like, I think it goes to sleep. Okay, so I want to say something about, there's a co-algebraic structure of the AB index actually and the CD index. So this is different. So, okay, so let's let KAB be a polynomial algebra in non-commutative variables A and B. So just think about polynomials in A and B where you can't switch the order around. You have to keep everything in whatever order they are. And so you can always multiply things together in terms of you just put them next to each other. That's concatenation. So there's something called a coproduct. So remember, products, you put things together, whereas coproduct, we're going to break things apart in a funny way. So if you have some kind of a word in A's and B's, V1 to Vn, we're going to look at all possible ways to replace one of the letters with a tensor sign. So just think of it as a formal thing. And we're going to extend it to this whole polynomial algebra by linearity. And it looks like the y in my by fell down. And I'm going to have to fix that. Okay, so for example, let's compute the coproduct of ABB. So let's cover up A. So we place that with a tensor sign. So that's 1 tensor BB. Cover up the first B in the second slot. So that's going to be plus A tensor B, plus cover up the last letter, and that's going to be AB tensor 1. So this is an example of a coproduct. And quite often, like, you replace the tensor sign with a variable. We'll see that soon. Okay, so this looks very complicated, but it's actually not. So Joni Arota came up with this idea of a Newtonian co-algebra. So let's say in the background, you have a vector space with some kind of product and some kind of a coproduct. And we say it's a Newtonian co-algebra if it satisfies this thing called the Newtonian condition. What is this? Okay, all this is a fancy way to talk about the product rule in calculus. So how do you do product rule? So let's look at the Sweeler notation for all this. So if you're applying a product, delta, a derivative rather, to a product x times y, how does that go? Well, usually you take, x times the derivative of y plus y times the derivative of x. Okay, so now we're just writing this way. So here I have the coproduct applied to x times y is the sum over x, all possible ways to break up x with respect to that coproduct. So you read this as x Wheeler 1 tensor x Wheeler 2 times y plus x times all possible ways to break up y. So x times y Wheeler 1 tensor y Wheeler 2. So the whole point is that that tensor sort of moves along and you can factor things this way. It's just a product rule. That's all it really is. Okay, so with Richard Ehrenborg, I proved that this polynomial algebra in A's and B's with concatenation and this coproduct does satisfy a product rule. It's a Newtonian co-algebra. All right, so let's bump this up to posets. So again, I haven't really defined posets, but think of it as a directed graph at nice levels. So I'm going to have my vector space be types of graded posets, and I can define a coproduct on this poset, which is you look for an element in it, and then you break it up into pieces, the interval from 0 to x, tensor with the interval from x to 1. And then there's a way to piece together two partially ordered sets. So you remove the top element of the one poset P, the bottom of Q, and you slice those up, and then you put one above the other, and then you just put a complete bipartite graph between them. It turns out that this setting also is a Newtonian co-algebra. This is due to Ehrenborg and Hetchy. All right, so given this posets on these polynomial algebra and A's and B's, it turns out that the AB index is a Newtonian co-algebra. So I'm just going to leave it like this. You know, you don't necessarily have to follow this, but here's the thing to focus on is the coproduct. And it says the following. It says that let's actually apply this coproduct to C. So remember, C was A plus B. So the coproduct applied to A, cover up the A, you're left with 1 tensor 1, plus the coproduct applied to B, that's also 1 tensor 1. So we get 2 times 1 tensor 1. Same thing with the coproduct applied to D. So D is AB plus BA. And again, we're going to use the product rule. So it's going to be coproduct applied to AB is A times delta of B plus delta of A times B. Apply the coproduct to B times A, B times the coproduct of A plus coproduct of B times A. And then the miracle arrives. So coproduct applied to B is 1 tensor 1. A times that is A tensor 1. Coproduct of A is 1 tensor 1 times B is 1 tensor B. Same thing here. And then you have the funny thing. A tensor 1 plus B tensor 1, A plus B is C. And the other one, 1 tensor B plus 1 tensor A plus B is C. So we get something that's always in C's. So the whole point is that there's something funny happening here. And so as a corollary, when we have these graded Eulerian posets, of which polytopes, face Lattice polytopes are an example of this, we also have this co-algebra homomorphism. Why is this an important corollary? So I want you to stare here. So this bottom part says the following. If you get some kind of messy expression that you're trying to understand, like that right-hand side, you can actually realize it as some kind of a coproduct, like a derivative, applied to the CD index. So this is good. It says that you can change messy formulas to nice formulas. So let me just mention one in passing, just to understand, say something about this. So for example, this co-algebraic structure of the CD index, with Ehrenborg, we looked at prism and pyramid operation, and we actually showed if you take a polytope and take its prism, like we had that hexagonal prism, you can find its CD index by simply taking the prism, the hexagon CD index times C, plus apply a certain derivative to this CD index. So this was shocking that this geometry was reflected in this derivation kind of stuff. So maybe I will, for time, I will skip sort of the rest of this because I really wanted to go. Okay, I could say something about inequalities. Again, there's all different inequalities that people are interested. So I will just skip that. Okay, so let's go to Whitney Stratifications because I wanted to make sure I could at least do this. So now we're like sort of saying, all right, we've looked at polytopes. What about something called Whitney Stratification? So we're going to start looking at the n-gon again. So here I have a hexagon. And if we wrote out the flag F vector, so these are, I have one empty face, n vertices, n edges, and F01 is 2 times n, because every vertex is incident with 2 edges. You massage it, get the flag H vector. You have these monomials encoding the subsets. You get the CD index of the n-gon is C squared plus n minus 2 times D. So you have that. And here I actually have an example of the face lattice of this hexagon. Here I didn't label it, but these are the 6 vertices. Here are the 6 edges. I have a line connecting anything that's contained. So for example, this vertex here is contained in two edges, that one there and that one there. This is the minimal element and maximal element. And what you do is you arrange your faces according to dimension. So this is called a partially ordered set. Okay, so here we have the CDNs of the n-gon. So notice I'm assuming that n is at least 2. What if I had a 1-gon? Well, what should this answer be? C squared plus, well, C squared minus D, actually, it should be. So try to do the same thing with the 1-gon. All right, here's a vertex, here's an edge. All right, I have one empty face, one vertex, one edge. Vertex edge pairs is 1. You do the flag H, totally falls apart. It's not symmetric. Like, what's going on here? Well, the problem is that this underlying poset is not Eulerian. I remember at some point I said in every interval, the number of elements of even rank has to equal the number of elements of odd rank. If you went from the interval from the bottom element up to E, there's one element at rank 0, one at rank 2. So that's 2 elements. That's the even ranks. Whereas that V, there's only one element at rank 1. So there's a problem here. So now we have to think something's wrong. We got to do this again. And the way to do this is we have to look at the local structure, what's going on. So notice here, this vertex, it doesn't really see one edge. It actually sees 2. If it didn't see beyond, as far as that vertex is concerned, it sees 2 edges, right? So this is called the link operation. So formally, you're at the vertex, you take a little sphere around it, a circle, you intersect it with the edge, and you would get 2 isolated vertices. Now, the Euler characteristic of 2 isolated vertices is 2. So let's actually use that. So I'm going to call these all barred things. So I have flag F vector bar, the barred version of flag F vector and flag H vector. Okay, so again, I have one empty face, one vertex, one edge, but vertex edge pairs, I have 2, namely this vertex sees that edge end and this vertex sees that edge end. So 2, you run the flag H vector, you get 1, 0, 0, 1. Symmetric. So now again, I encode that each of these subsets. You end up getting the AB index, AA plus BB. It turns out you can write this as a CD index, and you really do get C squared minus D. So this is working. So this is sort of shocking that this is working. Okay, let's play the same game with, this is known as the winking torus. So this is like the surface of a bagel, and you have a smiley face, except it's winking at you. You only see one eye and the smile. And here I actually have the face poset of this. So I have the empty face in the bottom. I have 3 vertices, namely the ends of the smile, V1 and V2, and then V3 is the eye we can see. I have the edge, which is between the 2 ends of the smile. And then the next level thing, the 2-dimensional faces, is actually the torus minus the wink. And then on top, I have the solid torus. In other words, the whole thing together. That's the maximal element. And so this is the analogy for face poset. This is very strange. If you're used to working with these things, you're not used to having these spaces. I mean, like here is something of level 1, and then it's sort of skipping. There's nothing level 2. It goes right up to this level 3. And that's okay. We're just going to arrange things by their dimension and see how this goes. And it turns out that if we start looking at chains of faces in this face poset, we're going to do this link computation. So let's actually do this here just to show you how this goes. All right, so let's look at the flag F bar vector. So empty face is 0, F0. Okay, so notice here, so I lied. I went a little too fast. So when I have a chain of faces, the first step, I have to compute an Euler characteristic. The other steps, I have to do some sort of link thing. So I went a little too fast. So the first step is the empty face. So I actually have to compute the Euler characteristic of the solid torus. It turns out that's 0. So that's a topological invariant. Okay, F0, there are 3 vertices, 1 edge, F1, F2. So what is that? F2 bar. This is counting the number of 2-dimensional faces, but we have to keep track of the topology. So really remember that 2-dimensional face going back, that was actually the torus characteristic polynomial, Euler characteristic of the torus minus the wink. So torus has Euler characteristic 0. The wink, you can actually take that smile and it can be deformed down to a point. So it's really that surface minus 2 points. So that's why there's a -2 here. F01, we have vertex edge pair. There's 1 here, 1 here. So it's 2 of those. Vertex 2 face pairs, this is a little different. So this vertex sees a 2-dimensional face. This one sees a 2-dimensional face. The eye also sees a 2-dimensional face. However, it sees it all the way around. When you intersect a sphere centered at that vertex and intersect it with the boundary of that solid torus, you would see a circle, but a circle has Euler characteristic 0. So you never see that part in the computation. So this is actually correct. So you write this all out, you compute the flag H vector with a bar on it. And again, we get symmetric. And so then here, these other 2 columns, I've written in what 3DC and what -2CD would contribute to whatever flag H entries. So it turns out here, the CD index is very, very different. It's 3DC minus 2CD. So one thing that happens is you no longer have non-negative coefficients. Here I have a negative. What does this mean? We really don't know. We have no idea. We do know that, notice that we don't have any power of C cubed like we did. What we were used to 1 C cubed in the case of any 3-dimensional polytope. And the reason is it has to do with the Euler characteristic. So that we can explain. But these other ones, we don't know. Totally unknown. So it turns out that these examples, the one gone, actually a polytope, the boundary of a polytope, this winking torus, these are all examples of something called Whitney stratifications. So this is a way you split up space that has bad singularities or sort of well-behaved singularities into pieces. They're called strata. There's something called the condition of the frontier. If you have 2 pieces that one intersects the closure of the other, and that's non-empty, that actually talks about some containment in the face poset. And then there's something called Whitney conditions A and B. You're not allowed to have fractal kind of behavior or like infinite wiggling. So the whole idea is that when we do these link computations, the local geometry is really well controlled. Okay, here I have the real definition. We skip that. So it's a fine print. Okay, and then these things occur actually everywhere, Whitney stratifications. It's sort of shocking when you start realizing this. What's interesting is that they actually do have applications to robotics and computational geometry. So these are things we really should be studying. And let me give you an example of what does it mean about a nice decomposition, nice stratification of things have to be well defined, the link. So this is the Whitney Cusp. So you should think of this as an infinite sheet of newspaper or paper, and it goes forward and then it goes back and it self-intersects in this way. So you can see this sort of curvy thing. If you poured like lemonade in the top, it would hold into it because it shrinks down to a point in the middle. All right, so if we just stratified this with just this, okay, this is infinite, but my picture looks finite. If we stratified it with this edge as one-dimensional strata, and then everything else as a 2-dimensional strata, it turns out that's not a Whitney stratification. Because the problem is that when we start doing a link computation, and if you start looking at what's the local geometry, it should be the same no matter where I am on this ray or line. And oh God, what did I just do? And it turns out, what did I just do? Okay, it's yellow. It turns out that it's not, because when you're up here, what do you see? you see a sheet, a sheet, a sheet, a sheet. You see four things. But as you shrink down to the origin, all of a sudden there's nothing in front of you and there's two sheets behind you. So this actually tells you to stratify this properly, we would have to actually split this line. We would have to declare the origin to be its own strata. And if we do that, then everything works great. It doesn't matter where you're standing on the strata, you're going to get the same answer. All right, it turns out all this Whitney stratification stuff, the face posets of them, are examples of something called quasi-graded posets. So I had an example there for the winking torus. The whole idea of things are in nice ranks, and there's something called a zeta bar function, which keeps track of, you have like nice weightings going on. So there is an Eulerian condition, a more general Eulerian condition. And when you study the incidence algebra, it turns out that this really is truly a generalization of classical Eulerian condition. Let's see, and then this just tells you how do you compute the AB index. The fact is that in this Eulerian setting, we have this flag F bar vector satisfies generalized dense Somerville relations. We have a CD index, and then Alexander duality, which you have in Eulerian posets, also works in this quasi-graded poset setting. And what we get is, as a corollary back to the geometry, for example, the winking torus, is that this, when you have a Whitney stratified boundary of a manifold, that the face poset is quasi-graded. It's this generalized Eulerian, and if we arrange elements by their dimension and we do a certain computation, we weight chains according to this length, things work out. So I mentioned some current work just so you can see some things that can go. I mean, a big open question is just to understand the coefficients of the CD index in general. We really don't know very much. I mean, Kalakaru he has results that he actually looks at a sequence of operators of sheaves of vector spaces. I find this very hard because I don't really know sheaf theory, and that takes a couple years to understand even just his statements. And I don't think that's a very compelling answer. At least I'm not compelled yet. I should point out again, in this Whitney stratified manifold setting, CD index can have negative coefficients. That makes it interesting. Finding linear inequalities holding among CD index of Whitney stratified manifolds, that's open. Finding minimization inequalities. I'll skip 4. And then Ehrenberg has a lifting technique for, if you know inequalities among F vector entries and more general flag vector entries, how to lift them up. And so he has various ways to do this. There's a lot of more I could say, but I just wanted to give you a taste of, you can actually get very deep. So thank you very much. Thank you for your attention. I will stop the share.
Thank you so much, Dr. Reddy. If everyone could please give a round of applause like some people are already doing, that would be great.
I see the floating hands. So are there any questions about anything? I did a lot. I mean, this is a many years work. So you shouldn't feel like, oh, I didn't follow everything. No, but there's certain things that you should feel like, oh, already F vector isn't known for four-dimensional polytopes. I mean, this seems to be something quite often in mathematics, that dimension 4 is tricky. And even like work that Richard Ehrenberg has done, he has found inequalities for flag vectors starting in 6-dimensional polytopes, but just there's still a lot more work to be done. It's shocking. So we need new ideas. So that's why it's quite good to go in some more general setting. Any questions on anything? Questions, comments, anything? I see the floating faces.
Yeah, maybe I'll ask a quick question
Sure.
about undergraduate classes that you think would recommend to better prepare for research in a field like this, just to get a nice background
Okay,
understanding.
so let me tell you, I think the best advice is take as much math as you can, because I'll be honest with you, my thesis was completely different, and it actually turned out I had something in my thesis which I had an open question, and I went to a conference in Montreal, and Richard Stanley said to me, oh, that conjecture follows immediately from the non-negativity of the coefficients of the CD index. And I looked at him and I said, Professor Stanley, what is a CD index? I had no idea. So it took me a year to understand that one sentence he said. So, I mean, as an undergrad, I would say take linear algebra. I mean, amazingly, a lot of people don't take linear algebra as undergrads, and that is a very good class to take. I wish I had abstract algebra. I didn't have that. So these are things I had to pick up in graduate school. And if you can, take topology, take algebra, take probability. I took that. I took an applied mathematics course. I mean, anything you learn, you're going to use. So again, the more math you learn, the more you'll have under your belt. And even as a mathematician, I have found that if I read a research paper, I say at the time, oh, this is so hard, and it hurts my head, whatever. I have to force myself to take notes to stay awake, but I always use it. It's really funny. It's like it becomes part of you, and then you start seeing connections. And I think, and you realize too, I think as a student, perhaps you don't realize it until you go to graduate school. And even then you don't realize is that you can be in the middle of a project and you actually learn as you go. I mean, I had a student who she wanted to work in topology, topological combinatorics. And I looked at her and I said, I don't really know this field other than I was at a conference and I heard a series of lectures from Michelle Wax on this in Park City, Utah. And I said, that's all I know, 5 hours worth of this stuff, but we'll learn it together. And that's what we did. So you should never feel like you have to know everything to solve problems, just learn as much as you can, but then realize you're going to have to learn more. I think that's the best thing. So don't feel like, because let's face it, you would have to probably live like 1,000 lives to learn all the math that's known right now, because there's a lot of mathematics. So you should just, pick the things that you really love to work in, and then you just do. So thanks for the question. Anything else?
Yeah, thank you.
You're welcome. Excellent question. I wish I had known that as an undergrad.
I have a question.
Yes.
You said that
Maria.
there were slides available for this talk.
Yeah. So if you go to my website, you will see the slides. So if you just Google Margaret Reddy, you have to spell Reddy correctly.
Oh, I'm on the page now.
Yeah. And if you go down, you'll see Kutztown, that there's a talk. I'm giving a talk hosted by Kutztown. And
okay.
Do you see the slides? It should say like slides.
I will find it. If it's on the page, I'll find it.
It's
Sorry,
definitely
I'm doing it on
there.
my phone, so it's
yeah. Oh,
okay.
I forget your phone. No,
sense.
it'll blow up your phone. Look,
Yeah.
it almost blew up my laptop.
Okay.
So yeah, it's definitely
Okay.
there. Yeah, because I went super fast. So you shouldn't at all feel like. Yeah, go ahead. I think somebody was asking another question. Thanks for the question. Anything else? Is Dorian trying to
I
say?
have one more.
Oh yeah,
I have one
go
more
ahead.
question. Sorry. Is there any text that you would recommend that could kind of talk about this topic?
Yes. In fact, it's so convenient. I'm at home because I'm right by my books. Let me
okay.
pull a book off my shelf. Okay, so to learn about polytopes is Günter Ziegler has a book. It's called Lectures on Polytopes. Okay, it says
Oh.
graduate texts in mathematics. Just ignore that. This is how I learned polytopes. And you're going to laugh at how I learned. So what happened was that Richard Ehrenborg and I, we met as postdocs, and we both got jobs at Cornell, 3-year jobs. And we knew Lou Belair was there and he loved polytopes. And we thought, we better learn what a polytope is. We don't really know. So we got this book because Richard Stanley told me read this book. And we got to chapter 0, which was on introduction. And you can see like almost every page has pictures. It's really a nice book. So it's very approachable. I mean, look at all the pictures. It's so excellent. And we made it through chapter 0. We were so psyched. And then one day we were walking around campus at Cornell and Richard Ehrenborg had said, gee, I wonder if the CD index is interesting to look at under geometric operations, because we learned about prism and pyramid and various things in here. And I answered, well, it must be interesting because it's geometrically motivated. And that's how we started understanding all this stuff. And Richard knew about co-algebras and Hopf algebras as a graduate student at MIT. And the fact that I had part of my thesis had to do with the CD index, thanks to Richard Stanley, I learned that. So the two of us knew the right pieces to actually put together. But this is a very nice book actually to learn on your own or with friends. I mean, that's actually what we did. So Günter Ziegler's book, Lectures on Polytopes. Someday I should write a book on the polytopes. Great question.
Thank you.
You're welcome. Anything else? These are great questions, like useful questions. Everybody's just like,
Well, if there's no further questions, I did just want to say most of the people have ducked out, but if you
That's okay.
didn't fill out, if you're in Kutztown AWM and you want service hours for attending, please fill out that form in the chat. And then also, I just wanted to say for next week, yes, it is next week, March 2nd, we'll be having the next lecture, which is using numbers for blind pool investing in venture capital.